In this video series, we want to have practical experience on electrical motors. I have disassembled these two BLDCs that used in fans. We will talk about each part one by one to have better insight. Why we use outer rotor, which permanent magnet is better to design in our machines, and what is the differences between these two stators. We also talk about the windings, the wires, how we choose fill factor and stator or rotor laminations. This is the rotor of this BLDC. Here is the central shaft, the magnets, the rotor back iron, and the load. The load is a fan and the blades are directly connected to the rotor back iron because this is the outer rotor topology and the stator is inside the rotor. From the appearance of the magnet, we can guess this is the ceramic or ferrite magnet. Between four main types of permanent magnets like neodymium or samarium cobalt and all nickel, the ferrite or ceramic magnets are the most affordable type in low-cost fans. Other types of magnets, like this neodymium magnet, usually have a shiny skin or coating on themselves. This neodymium magnet is more powerful and of course it's more expensive than this ceramic magnet. Now let's find out how many poles that this magnet has, because in many motors you can see there are separated magnets are assembled in the rotor, but in this cost-effective design the rotor has a solid single part magnet and it is magnetized in different directions. To find out the magnet's directions, I will use this small iron ball. If we put it in the magnet, we see that the ball will take its place in the center of north or south poles of the magnet. So we have one pole here, one pole here, 2, 3, 4, 5, 6, 7, and 8 poles in this solid magnet. It's a good way to understand the magnet's direction or the center of the south or north pole of the magnet. You can see the ball will take its place on the center of the pole and you can't change the place until it finds the next magnet. Now let's simulate the geometry that we were discussing. In the ANSYS Maxwell, we want to model the geometry of magnet with iron ball and find out where the iron ball will stop, in the middle of the pole or in the space between two near poles. It's a very good example to start simulation with ANSYS Maxwell, and I will try to describe as much as possible. I will open a Maxwell 2D. The first step of simulation is to create the geometry of the magnet or the motor core and winding. The first step is to draw the geometry. We remember the geometry of the iron was a hollow cylinder. So I will draw a circle in 2D geometry, select the circle for drawing. We need to define the center point. With clicking on tab, I will select 0, 0, 0 for the center. And as we remember, the inner diameter of the magnet was 7 centimeter and the outer diameter was 8 centimeter. So the radius of the inner part of the magnet was 75 millimeters. To see the whole geometry that you draw, you can click on Fit All or press Ctrl plus D. Inner diameter, and I draw another circle with 0, 0, 0 and 5 millimeter of magnet thickness. Now we draw the two circles. We can subtract them from each other. First, select the outer circle, and then with pressing Ctrl button you can select the inner. Find the subtract and click on subtract. You can click on OK, and now you have the shape of the magnet with 5 millimeter thickness. We knew that we have 4-pole magnet and 8-pole magnet. Let's start with simulating the 4-pole magnet. We know that in these magnets we have N pole in the inner diameter or S pole on the outer, or vice versa, the S on the inner diameter and N on the outer diameter. So we have to divide this unified circle to 4 poles. To do that, I will draw a rectangle to separate these magnets. Look what I will draw. I will draw a rectangle in the center. And now let's copy that with 90-degree rotation. Click on duplicate around axis. With 90-degree rotation and creating a duplicate of them, I can subtract these two rectangles from the circle again. Now we have 4 different poles, but it's just a circle. We didn't assign the material and the properties of the magnet yet. The other thing that is needed to be done is when you select each of them, the whole part will be selected because they are not separated yet. Just we subtract a rectangle from them. To make them separated, you have to right click on the page, go to the edit boolean and separate bodies. Now we have 4 different parts for the magnet. It is the geometry. Now let's assign the material. First of all, to be able to recognize each part, select the first magnet and rename it in the properties box. You can name it as, for example, N1, and the other side you can select it with N2. Now select this as NS1 and this one as S2. To have a better visual picture, you can recolor them as blue and red too. The S poles are red and the N poles are red and the S poles are blue now. Now let's go to select the material of the magnet, the properties of the magnet, and the direction of magnetization. We know that in cylindrical magnets, the direction of the magnets are in the R direction in cylindrical coordinate system. In XY coordinate system, if we magnetize a magnet in one of their direction, when they rotate, the magnetization direction will change. But in the cylindrical coordinate system, we can use the R direction and it is not changing when it rotates. We know that these two magnets are N poles, so we have to click on them, select assign material, and go to the magnetic properties of the magnet. We have different types of magnets like neodymium bore, like ferrite magnet or ceramic magnets, all nickel, and samarium cobalt. For these magnets, because we know that the and the FEB magnets are like silver color, and these magnets were black. We know that they are ceramic magnets. So let's select this ceramic magnet and edit the material. In the material setting, you can change the material coordinate system type. Use the cylindrical system and you will see the magnitude will remain the same, but the vector of the magnetization will change from XYZ to RFZ when we change the cylindrical coordinate system. We want these magnets to be directed in the R component, +1. We choose 1 as the vector and the magnitude is 190 ampere per meter. In the magnet properties, we will choose the coercivity, residual coercivity for magnet as the power of the magnet or strength of the magnet. Let's select OK, and select these two magnets. Remember, the polarity of these magnets are opposite. So we will click assign material, ceramic. We have to clone the material, and in this clone material we can rename it as a S direction, and the direction of the magnetization will be -1 in the R component. Click on OK, and now we can see we have two different materials, ceramic 5 and ceramic S. Let's rename it as ceramic N. Okay, we have two different materials, and for a good simulation we have to create a good region. For the region we need a bigger circle around the main geometry. We will draw a circle, then click on select mode, select the edge, select the outer edge of the circle and assign boundary. We know that we have to assign vector potential as the end of the simulation, end of the geometry. Now again click on select mode, go to the object, and you can hide this object from the simulation. We have to draw two other geometries again. We know that this outer rotor BLDC has a very slight back iron around the magnets too. So I will draw a circle around the magnets with 1 millimeter diameter higher. Subtract these two from each other, and we know that this back iron is made of steel. So I will click on assign material and choose steel. We have many videos about the properties of the steel. You have to check the properties of BH curve. If you have iron, steel, or ferrite, you can change the BH curve. Click on OK, and let's draw the iron ball. The iron ball was very close to the magnets, so I will draw the iron ball here and choose the material. Let's do another thing for material. We know that this is the outer region, so we rename it as region. This circle was the ball that we used, and this part was back iron. We know that we will have a force on this ball, so to assign the parameter to measure the force or torque, we have to select it, go to the assign parameter and choose the torque, because we know that the magnets will attract this ball, but the thing that cause this ball to stay in a place or run to another stable place is the torque that's exposed to this ball. So I will assign the torque to measure the available torque on this ball. We are using the magnetostatic simulation. In the magnetostatic simulation, you can measure the forces and torques of the magnets or the winding with DC currents. We can't model the sinusoidal waveform or pulsive waveforms in the magnetostatic, but for this simulation, magnetostatic is good enough. In the magnetostatic simulations, all the parameters, force, inductance, or torque will be calculated for 1 meter axial length. So if we have a smaller axial length, we have to calculate the inductance or load or torque with relation between the real axial length and 1 meter axial length that simulation use. The other important job that we need to do is to create a mesh, a fine mesh on these materials. We know that these magnets have 5 millimeter lengths. So I will select all of them and assign inside mesh operation with lower than 1 millimeter, for example 0.8 millimeter, to have a meshing operation. The other task is to assign solution setup. Right click on analysis, go to the add solution setup and add the parameters of the simulation. The default values are good enough. For better convergence, the simulation will refine the mesh each pass, and the maximum number of iteration or passes will be 10. It's good enough. To check if you did all the simulation tasks correctly, you can go to the simulation tab and check the validate. If all of the parts are checked, you can analyze. But we remember that we turn this ball around the magnets and it will stay in some points and run from some points. We want to understand which parts are the stable parts, which places are the stable points, and which places were the points that the ball will run from them. To do that, I will select this ball and rotate it around the magnets. First, I will rotate it, for example, 90 degree and simulate it. And I can move it, for example, change this rotation for 45 degree and do the simulation. Instead of measuring this torque in different simulation with different rotation, I will click on this rotate, and instead of the angle of the rotation, I will use a parameter like rot angle. If I click on enter button, it will add a variable for me and the initial value will be 45. Now I can simulate this variable and change the value of it to see the different torques. If you click on the name of simulation, you can see the variables names. If you change it, you can see the place of the ball will change. Now instead of one simulation, I want to add a parametric simulation and sweep this parameter from 0 degree to 360 degree with 10 degree steps. If you click on OK and go to the table, you will see we will have 37 different simulations, and all of them can be calculated in a single analyze and see the whole results together. Click save the simulation somewhere and the analyzing will be a start. It will take a while to see the results, and after that we can extract the stable and running points. After the first simulation, as I made a mistake in assigning material. I forgot to assign the ball as a iron part or a steel part. I can just drag it to the steel part, and for better and softer diagram, you have to make the steps of rotation as 5 degree instead of 10 degree. The whole the 5 degree will create 73 simulation, and after it analyzed I will demonstrate the results. Now the simulation is finished, and let's consider the results. To plot the results, you have to right click on results, create a magnetic report, rectangular plot, and choose the primary sweep or X axis as rotation angle, because we want to plot the torque versus rotation angle. If you click on OK, it will draw the torque versus rotation angle. Our geometry doesn't have 1 meter axial length, and it is 25 millimeter. So to have actual results, we will multiply the torque by 0.25, and it's 25 millimeter, and changing the torque value for 1 meter to the value of the torque for 25 millimeters in axial length. The value is not important for us for this simulation. We wanted to understand the points that the ball will stay steady, or stable points for the ball. We know that if the ball is fixed and doesn't change the place, in that place the torque will be 0. There is no torque to change the place of the ball. But we modeled 4-pole geometry. Here we have a 4-pole geometry. Why we have 8 zero crossing torque? Here we have 1 zero crossing, and here we have 1 zero crossing too. It's a very interesting point. Actually, in this point that is happening here, you can right click on the page, go to the marker, add a marker here in 45 degree. Here in 45 degree we have a zero crossing and 0 torque too, when the ball is here in the 45 degree, in the middle of the magnet. When the ball is between 2 magnets, but both of them are not a stable point. Look at this point. Here the torque is 0, but if you move forward, if you move a little bit forward, the torque will be positive. You move in the positive direction and the torque will be positive. It forces the ball to change the place. You move forward, the torque is forward, so the ball will be here, will stay here. So it's not the stable point. The torque is 0, but it's not stable, because if you move forward, the torque will be forward too. If you move backward, the torque will be minus and will force the ball to change the place. But here, in this point, if you move forward, the torque will be negative. So it will force the ball back in the place. If you move backward, if you go in negative direction of the circle, the torque will be positive. So it will force the ball to stay in this point. So the stable points is 0, 90 degree, 180 degree, and 270 degree. This is the 360 degree, and it's exactly equal to this point. So we have 4 stable point for this ball and 4 zero crossing torque, but these points are not stable. These points happens when the ball is exactly in the front of the center of the magnet. That's why when we push the ball from here a little bit, it will resist against changing the place. But when it goes here, it will automatically fall in this stable point. And it was a very interesting point that I got from this simulation. So the stable point of the ball is not in the center of the magnet. It's in between two different magnets. I hope you enjoyed this simulation. If you want to stay updated, please click on subscribe button and hit the like button of the video. Try to simulate the 8-pole geometry by yourself, and if you had any problems, you can ask your question in the comment section. In the next video, we will simulate the stator and winding of this BLDC motor too, to be able to simulate the torque and speed of the magnets.